To start the discussion of electromagnetism, we first look at the difference between alternating current and direct current. The green line on the screen is 3 volts of unvarying DC from the power supply. The yellow line at the moment indicates nothing, but the power grid induces a 50 Hertz voltage into our bodies all of the time, like this. In fact, anywhere on our body is having 50 Hertz of voltage induced into it. Our body is simply a sack of salty water with the same pH and salinity as the ocean, so it conducts electricity well. If you're in doubt about the process, you can see that when I hold the power cord, the voltage goes up. This process is defined by the equation EMF, or voltage, is equal to delta phi on delta T, or change in magnetic flux over time taken with a negative sign in front. So where does the magnetic flux come from? Every moving electron produces a small magnetic field. 1 amp is 1 coulomb per second. That's 6.25 times 10 to the 18th electrons per second. So we should be able to detect the magnetic field generated by a large current. This switch mode power supply will produce a large stable current of 3 amps at 0.5 of a volt. These rods will easily carry this much current. We'll use this compass to determine the direction of field using only one rod. Placed below the rod, the compass moves in the anti-clockwise direction. Placed above the rod, the compass moves in the clockwise direction. The implication here is that it goes one way on the top and the other way on the bottom, which means that the magnetic field around a long straight conductor is cylindrical. If we make our right hand in the shape of a cylinder with the thumb in the direction of current flow, then the fingers are in the direction of the magnetic field. The two-dimensional convention for this is that a cross indicates the direction of the magnetic field going into the page, and a dot indicates the direction of the magnetic field coming out of the page. We can remember this if we use a rocket. If we look at the nose of the rocket, it appears like a dot coming out of the page. If we look at the tail, it looks like a cross going into the page. Here's an example using current in the left direction. For 2 parallel rods with a current flowing in the same direction, the compass is not deflected. In this example, both currents produce a magnetic field in the anti-clockwise direction. This cancels the magnetic field strength halfway between the rods. For the example, when the current is flowing in the opposite direction, the magnetic field strengths add and the compass is deflected. The magnetic field strength can be greatly increased if a conductor is coiled in such a way that the individual strands add to the magnetic field strength. So here's a large model of a coil. The right-hand rule for coils is that if you put your fingers in the direction of current flow, the thumb points in the direction of magnetic field. The old rule still works, for the rule for straight conductors, so you put your thumb in the direction of the current and the fingers go in the direction of magnetic field. But most coils are far too small, like this one. This is a relay with a timer sending a voltage to a coil which produces a magnetic field which closes a spring switch which turns the lead on, then releases it, which turns the lead off. The compass is a bit of a blunt instrument for checking the magnetic field on a coil. But fortunately, you have a device, a magnetometer, on your phone. The trick is to find out exactly where the magnetometer is located. To do this, take a section of metal coat hanger and move it slowly over the surface of the phone until you find a spot where the magnetic field strength is maximum. Then mark it with a sticker. To measure the field strength, place the phone over the end of the coil with a sticker on top of the area you want to measure. Although this device is very small, it can be scaled up greatly. Much of the robotics manufacturing industry is based on this electromagnetic principle. To determine the contribution of delta T, we'll use the oscilloscope. This magnet will be dropped through this coil from a height of 5, 10, 20 and 30 centimetres through these tubes. The x-axis is time and the y-axis is voltage. See if you can guess the shape of the voltage output. The red end is north. 1, 2, 3, drop. So there's a peak and then a trough. Let's reverse the magnet. Now the yellow end goes first. 1, 2, 3, drop. Now there's a trough and then a peak. The reason for this is the magnet has to approach the coil and then leave it. The right-hand rule dictates that in the middle the voltage will be 0. Notice also that the leading perturbation on the oscilloscope is wider than the trailing one. This is because the magnet moves more slowly as it begins to drop. Now let's get some data. 30 centimetre again. $20 centimetre. 10 centimetre. 5 centimetre. Now we can turn the data table into a graph. We have 75 milliseconds and 395 millivolts, 80 milliseconds and 305 millivolts, 90 milliseconds and 205 millivolts, 102 milliseconds and 140 millivolts. Looking at the graph, it's obvious that the less time the magnet spends in the coil, the greater the voltage. This is embodied in Faraday's equation. We have EMF is is equal to negative n d phi dt. And you can see that the smaller dt becomes, the greater the voltage becomes, because dt is on the bottom line of that equation. This leaves us just with a negative sign to discuss. This is a magnet, and this is a piece of steel machined to the same diameter and the same length as the magnet. This is aluminium tube, not magnetic, and this is a viewer to allow us to see what goes on inside the tube. We drop the steel. We drop the magnet, and the magnet falls more slowly. What's going on? The tube's not magnetic, it's aluminium. What's going on is a three-step process. 1, the magnet produces a current in the aluminium. 2, the current produces a magnetic field that opposes the drop of the magnet. 3, the magnet slows down. This is Lenz's law. It's what gives Faraday's equation the negative sign. Imagine that the field was produced in the opposite direction. The magnet would speed up, and we'd have a very powerful weapon that defied the law of conservation of energy. This doesn't happen. Finally, the n term in the equation is an accounting term, which keeps track of the incremental increase from winds in a coil to increase in the resultant EMF. I hope you find this interesting and helpful, and all the very best.